Hey everyone, this is going to be a video summarizing electron configurations. Electron configurations is a pretty broad topic. There's lots of different ways to represent electron configurations. So this is just going to be a summary kind of overview of all of them. And there's more details to this, and I'm going to refer you back to the course packet. Um, yeah, so there's more details. What I'm going to go over, this is going to be kind of rushed because, like I said, it is a lot of material. But we're just going to kind of do nuts and bolts. What do these things look like when we're asked to draw them or represent them? So just some basics. Electron configurations means how the electrons are organized within an atom or an ion. And the electrons exist within a region of space, within various regions of space within the atom. Those regions of space are known as orbitals. And the orbitals come in 4 different flavors, S, P, D, and F. Don't worry about what the letters stand for. They kind of just are. They do stand for things, but they don't mean anything anymore. Long story. Anyway, the orbitals that you're going to run into are the S orbitals. They're always spherical. All right. The P orbitals, there's always 3 of them. The one that sticks up and down and kind of looks like a peanut. The one that's sideways and kind of looks like a peanut. And the one that's coming out of the screen at you. I know it doesn't look like it is, but you have to pretend. These are all at right angles to one another. Those are the p orbitals. Then there's the d orbitals. The d orbitals are a bit of a nightmare because, one, they're hard to draw. They're basically doubled up p orbitals. There's always one that's like that. There's one that's like this. There's these two, but sideways in the other third dimension, which I can't draw, so I'm just going to draw them again. And then there's this really weird one that's kind of a mathematical nightmare. It's just what it is. When you take quantum mechanics, you'll learn about this one. It kind of has this like donut shape around the middle. Just trust me. So anyway, those are the d orbitals. There's the reason I'm sketching these out, and there are better pictures on the internet. So please just take a look at those so that you have a better mental picture. But there's always a single s orbital each time you encounter them. There's always 3 p orbitals, and there's always 5 d orbitals anytime you encounter them. These exist in with various numbers in front, designating the size. S's run from 1s, 2s, 3s. The p's start at 2p, 3p, 4p. The d's start at 3d, so they go 3d, 4d, 5d. And then there's also the f's, which we're not dealing with. There's always 7 of them. They start at 4. 4f is the first one that exists. And again, we're not getting into the whys and hows. That's just the way it is. All right. So with that very brief introduction, let's look at some nuts and bolts of how you draw and represent these electron configurations. The first one we're going to talk about is orbital diagrams. Those are sometimes called arrow diagrams, where each electron is represented as an arrow. So we're going to start with carbon. And for carbon, oh, by the way, this is asking for the ground state electron configuration. Ground state is what you would kind of think of as normal. In other words, all the rules that I'm going to teach you are for ground state electron configurations. So if someone asks you for an electron configuration or a ground state electron configuration, it's the same thing. It's the lowest possible energy one. All right, so carbon, if we go to the periodic table, carbon has 6 protons. And that means a neutral carbon would have 6 electrons. All right, so going back to like the second day of class on that one. So we're dealing with 6 electrons. So the way these fill up is we start at the 1s. Each orbital can contain 2 electrons. One has spin up, one has spin down. What does spin mean? It's another thing we're glossing over. Don't worry about it. It's really complicated. But we're going to, and you can only have 2 electrons in a single orbital. That's allowed to exist in a single orbital. So each orbital will have 2 electrons. One of them will have a spin up, one of them will have a spin down. We represent them as an up and down arrow in these orbital diagrams. The next orbital higher in energy is the 2s, so it's going to have 2 electrons. But the next orbital above that are the 2p orbitals. And again, with p's, there's always 3 of them. And these orbitals all have the same energy, which means they're all equal in energy. The technical term is degenerate. And these degenerate same energy orbitals, anytime there's the chance to fill electrons in here, we're going to put one in the first orbital and an additional electron with the same spin in the next orbital. We're never going to pair up in degenerate orbitals until we have to. All right, so the next one down is nitrogen. If you look at nitrogen on a periodic table, it's got 7 electrons. So it's going to go 1s, 2s. Now we've got 3 more electrons to go. So we're going to go here, here, and here. All 3 up, 1 to each orbital. Now when you get to 8 electrons, as in oxygen, now what do we do? Well, now we're finally, so this is our 5, 6, 7, and our 8th electron is going to go here. It's going to be paired up. And then if you had a 9th electron, like for fluorine, it would go here if you had fluorine, okay? And then if you had neon, it would go here, all right? I'm going to erase that because it's probably going to confuse people. But so that's the electron configuration for oxygen, all right? This business about putting each of the electrons separately in orbitals before you start pairing them up is known as Hund's rule. And Hund's rule just says that the electrons are lower in energy if you space them out one to an orbital with the same spin. Sometimes this is known as maximizing the spin that's possible. And so that it turns out, again, for weird quantum mechanics reasons, that's the lowest energy state. All right. So let's do one additional one here. Let's do sodium. When we look at sodium on the periodic table, it's over here. It's got 11 electrons, or 11 protons, and it's neutral, so it's 11 electrons. So now we're going to go, so we got 11 electrons to fill. So 2 in the 1s, 3, 4, 5, 6, 7, 8, 9, 10. We got 1 left. The next highest orbital in energy is the 3s. Okay. So far, hopefully so good. Let's look at some slightly more complicated ones. Let's look at iron. So iron, if we go to the periodic table, iron has atomic number 26. So neutral iron will have 26 protons as well as 26 electrons. So we got 26 electrons. So we've learned this kind of basic orbital energy: 1s, 2s, 2p. Now I'm going to get lazy and just draw the single-sided arrows, and that's okay. That's 10 electrons so far. 3s. Now we're at 12. Where do we go after 3s? 3p. Sorry, I'm getting ahead of myself. 13, 14, 15, 16, 17, 18. Now, after 3p, the orbital energy gets a little weird. And the way we remember what the orbital energy is, you can go look it up, or you could memorize the list, but there's a little helpful way to remember what it is. What we're going to do, I'm going to draw this in a little different color. We write out the orbitals that can exist in this kind of stair-step fashion. Oh, I did it again where I didn't give myself enough space. I always think I've got more space than I do. I have the same problem on a chalkboard. All right, 5s, 5p, 5d, 5f, 6f. Okay, so we just kind of write these out in stair-step order like this. And what we do is we draw lines through them, so going like this. So 1s is the first orbital, 2s is the second orbital in terms of energy. The next highest is 2p, then 3s, then 3p, then 4s, then 3d, then 4p, then 5s. So this is where it gets all wacky, right? So you go 3p, you would think after the 3p, the next would be 3d, but it turns out the 4s sneaks in there as the next highest, then the 3D, then the 4p, then the 5s. It's actually more, and then 4D, 5p, 6s, blah, blah, blah. It's actually more complicated than this. That's a topic for an advanced course. So when you get to PChem or inorganic, you'll learn this, okay? Anyway, back to the problem at hand for iron. We're up to 18 electrons here. We've still got to get to 26. So after the 3p comes the 4s. So 4s is next, 19, 20. Now after 4s comes 3d. And remember, with d's, there's always 5 possible orbitals, all degenerate. So again, Hund's rule says that for degenerate orbitals, we put 1 electron in each first before we pair. So we're up to 20 electrons, so we got 6 to go. So 21, 22, 23, 24, 25, and 26. All right, so that's going to be the electron configuration for iron. Germanium, up next. Germanium is over here. It's got 32 protons and 32 electrons when it's neutral. So it's going to be all the same. 1s, 2s, 2p, and yeah, these get kind of boring, and there's a shortcut. We'll get to that in just a second. 3s, 3p, 4s. Now I gotta move this guy again. Oops! Oh, no, didn't mean to do that. I want my diagram. That's the one. I still can't quite. One of these days I'm going to be good at this. And then there'll be something better, and I'll have to switch technology again. All right, just squeeze this under here. And we got, after 4s comes the 3d. 1, 2, 3, 4, 5. So this is 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Now after the 3d, according to our diagram, 4p is next. P's, there's always 3. And we're up to 30, we got to get to 32. So 31, oh, come on, 32. That's it. That's the electron configuration orbital diagram for germanium, okay? So the key thing here is that you need to be able to draw this little diagram here to help you remember the orbital energies. And so I would really just, whenever you're doing your homework or practice problems, I would just draw it off to the side, even if you have it written down somewhere. Just draw it, make sure you know how to draw it. It's not that hard, but it's good to practice, okay? All right, so now for the shortcut. Draw the electron configuration orbital diagrams of the highest occupied orbital. In other words, the last orbital that has any electrons in it for molybdenum. So let's go back over to our periodic table. Molybdenum, element 42 over here. Notice that it's in this middle part here, which on my periodic table is colored blue. And actually here, let's draw this out before we do anything. So you can use the periodic table because there are these little patterns to how electrons fill in the periodic table. And it turns out that if you think of the periodic table like this, everything on this left, these first 2 columns, their highest occupied orbital is an s orbital. Everything in this right part of the periodic table, they end in p orbitals. Everything in the middle ends in d. Everything in this 2 rows down below, or at least the way we normally draw it, are end in f's. We're going to mostly confine our interest to the sp and d orbitals. The f's have their own issues, but and you will cover in advanced coursework, and we're going to semi-ignore them for now. But anyway, so for molybdenum ends up here in the middle, and it's in this D part of the periodic table, and we are going to then look at which row it's in. It's in the second row of the D orbitals. This top row where we have scandium and titanium, vanadium, these all represent the 3D orbital, because that's the first time D orbitals exist, is the 3D. So everything here where we have yttrium and zirconium and et cetera. These are going to be the 4Ds, and then we're going to count 1, 2, 3, 4 over. So this is going to be 4D4, right? So molybdenum is going to be 4D4, and I haven't actually introduced this notation, and we're asked to draw the other one anyway, so let's stick to what we're being asked for. 1, 2, 3, 4, 5, 4D, 1, 2, 3, 4. All right, so strontium is over here on the left-hand side. It's in the second column of the s orbital region of the periodic table, and it's the 1, 2, 3, 4, fifth row down, so that's 5s2.